Okay, well, hello and welcome. Uh, I welcome you all to this very special class, which is going to last for about half an hour or so. And well, it's just to get you acquainted with actually what's actually a problem-solving category of Olympiad type problems. So we are just about to begin in a couple of minutes. We are waiting for other participants to join in. And we will begin in a couple of minutes. So just stand by and bear with us till other participants are joining. Okay, right. So, well, hello and welcome everyone. I welcome everyone who's here. And in the next half an hour or so, what I'm going to do is that I'm just going to take you through problems, which I'm hoping that you will find them interesting. Whether you are able to solve it, you're not able to solve it. Obviously, I'm hoping that you will at least admire the problem for what it is. And well, what I'm going to do is that obviously I'm going to solve those problems. And apart from solving those problems, I'm going to give you pointers that where to go after tackling that problem. So yeah, so in fact, so so coming back to the point, in general, what we do with a given problem is that we just don't solve it. We sort of torture it. We generalize it. We essentially strip the problem of its inessential details and then try to solve it. So in this session, that you will see that I'm going to do the following, the list of things which I've just said. And it doesn't really matter that which grade you are in. It doesn't matter you're in grade 7th or grade 6 or 8 or 9 or 10 or 11 or 12. I'm absolutely convinced that you will be able to understand the underlying logic behind these problems. And I'm also fairly convinced that no matter which grade you're in, from grade 6 to grade 12, if you haven't seen these problems, then if not stupefied by the problem, you're going to admire them in some sense. So without much further ado, I'm just going to deep dive into the problems. And in fact, I have listed those problems one by one and they come in increasing order of their difficulty. All right, so the first problem says something like that, and it doesn't really matter that which uh, which of the which grade you are studying in, and I'm pretty sure that you can make something out of this problem. And the problem, so I'll really, so at this point, might I add that I'll really appreciate if you can please switch off the video. Uh, should you have any question, we'll be happy to entertain that in the chat box. And I believe that I have Akshita with me, and we are going to entertain all the problems that you shoot at us and in the comment section. And so, yeah. So here's a question which says that there are a group of 5 people, and uh, 2 people are either enemies or they're friends. And they say that no 3 of them are friends of each other, and no 3 of them are enemies of each other. So then they say that prove that every person in this group has exactly 2 friends. So there are 5 people, and any 2 are friends or enemies. So should you take any 2 people, either they are going to be friends or they are going to be enemies. Um, no 3 of them are friends, so there are no 3 friends. So you can't have a group of 3 people who will be friends. So A is a friend of B is a friend of C, and C is a friend of A. This is not going to happen. So what they're saying is that prove that in such a group, every person must have 2 friends. Right. So what I'm going to do is that we essentially start with 5 people, and for a matter of convenience, I'm going to represent these 5 people by 5 dots. These dots are called nodes. Doesn't matter really. So call this as person 1. Call this as person 2. And call this as person 3. Call this as person 4. And let this guy be person 5. Uh, so what we know is that if you are going to take any 2 people, they're going to be friends or they're going to be enemies, right? And they have already stated that 2 people are friends or enemies. That's true. So if you're going to take any 2 people, so P1 and P3, they are going to be friends or they're going to be enemies. P1 and P4, they are going to be friends or they're going to be enemies. P1 and P5, they're going to be friends or they're going to be enemies. The same goes for P1 and P2. And what we have also been given is that there are no 3 people who are friends of each other or enemies of each other, right? And we have to prove that exactly every person has exactly 2 friends, right? So what I'm going to do is that I'm going to join 2 people by a line and call that line as F if they are friends. And I'm going to join 2 people by a line and call that line as E if they're enemies, right? So if I were to join a P1 and P2 using the line E, it means that P1 and P2 are enemies. If I were to join P1 and P2 via line, and if the line reads F, then it would mean that P1 and P2 are friends. So I'm hoping that my direction of attack is clear. Now think about it. Think about this problem with respect to the person P1. Since apart from P1, there are 4 other people, P5, P4, P3, and P2. So you agree that there will be 4 lines that will emanate from P1. That means that there will be 4 lines that will originate from P1. Why? Because P1 must be friends or foes with P2 and P3 and P4 and P5. I'm hoping that we are clear at this point, right? So what we have to prove is that exactly two of them are friends and exactly two of them are enemies. So I'd like you to consider the case that what happens if, say, that P1 has three friends. So suppose that we take the case that P1 and P2 are friends. So we join them via line segment and we call them friends. Suppose that P1 and P5 are friends. And suppose that P1 and P4 are friends. So suppose that if we were to say that, in fact, no, well, P1 doesn't have two friends, P1 has in fact three friends. So what would happen then, right? So the next which I'm going to ask you to think of is that, what about the line connecting P4 and P5? Well, if you are going to say that P4 and P5 are friends, then there's going to be a contradiction. Why there's going to be a contradiction? Because if these two guys are going to be friends, then these two guys are friends, these two guys are friends, and these two guys are friends. So which means that a group of three people are friends of each other, and which cannot be true because that's in fact a contradiction, right? So which essentially means that they have to be enemies. Okay, then I'll ask you to consider the line joining P2 and P5. So if you're going to say that P2 and P5 are friends, then we have a problem. What we have a problem is that these guys, P1 and P5, P1 and P2, P2 and P5, all three of them will be friends of each other because these two are already friends, these are already friends. And if you're going to say that they are friends, then a group of three people are friends of each other, which means that we will run into a problem. So they must be enemies of each other. Okay, so what I have considered is that P1 and P2, now consider about what will happen to P2 and P4. So P2 and P4 must mean something to each other. So if they are friends of each other, if they are friends of each other, so say that they are friends of each other, then we have a contradiction. Why we have a contradiction? Because look at this triangle. This says that P1 and P2 are friends, P2 and P4 are friends, and P1 and P4 are friends, which is a contradiction because it says that no three people can be friends of each other, right? So then you might argue that, well, P2 and P4 are friends. P2 and P4 in that case are in fact not friends, but they're enemies. So if they're enemies, then I'll ask you to consider this triangle, P2, P4, and P5. Well, these two guys, P2 and P5 are enemies. P4 and P5 are enemies. P2 and P4 are enemies, which is again a contradiction because we have been told that no three people can be enemies. So which tells you that indeed P2 can't have three friends. And I'll leave it to you to figure out that how P2 can't have four friends. The question that P2 can't have one friend or P2 can't have zero friend is the same as asking that P2 can't have three friends or P2 can't have four friends. Why? Because they're symmetric. Think about it. If P1 has one friend, then it means that the person P1 has, in fact, three enemies. The problem regarding three enemies, someone having three enemies and three friends will be similar, right? So we are not going to do it again. So we have proved that a person must have exactly two friends. Now, if you're interested in what we have just done, so this is an elementary idea from graph theory. This is an elementary idea from graph theory. And graph theory is kind of nice and it allows you to solve problems which do not seem like mathematical in the first instance. So, in fact, this problem was taken from Indian Statistical Institute examination 2007, and they were asked to prove this. And we have, in fact, successfully proved this. So now I'll take you to another puzzle. And in fact, I'll give you a couple of minutes to ponder over this problem before I eventually give you away the solution. So why don't you go ahead and solve it? Always bear in mind that mathematics is never a spectator sport. So why I'm encouraging you to solve it, despite this being a demo class, another class that you will eventually attend, is because of the fact that, well, the idea here is that you should be able to attack problems by yourself, right? And unless you can't do it, it will be difficult for you to be able to solve problems in examination. So yeah, I'll just give you a couple of minutes, and that will be it. Okay, right. So just take one more minute to attend this problem, and then we will dive into this problem. Can you see? And in fact, I'll ask you to identify that. Can you see that there are structural similarities between this problem and the previous problem? So it says that in a group of six people, there are always three people who either all know one another or all are strangers to one another. And at this stage, I'll ask you that, can you identify that there is some similarity between this problem and the previous problem? Well, if you can, then well, it's a great feeling. In fact, I'll argue that it's always a great feeling to be able to identify a new problem in terms of the problem that you already know how to solve. Because come to think about it, not every problem demands our attention, undivided attention, and that we should attempt it right from the first principles, because that would make uh, that would make everything very difficult. That if everything is new to us, every problem is a new problem, things will be pretty difficult in the world, right? So what we try to do is that when you're going to ask me to solve a problem, then the question which I'm going to ask to myself is that, have I solved a similar problem before? And if I have solved a similar problem before, then I would try to, if not emulate what I have already done in the previous problem, so at least uh, try to think of the style in which I solved the previous problem. So try to think of the previous problem. And the next question which I'm going to ask of you is that, can you think of the way in which this problem can be cast into the previous problem? And at this point, I'm hoping the answer to that is yes. So let me try. So they say that prove that in a group of six people, uh, there are always three who all know each other, or all strangers who do not know each other. Like, so that's the fundamental proposition about this problem. So in a group of six people, you will be able to find three people, either all three of them should know each other, or some three of people who do not know each other. First of all, I'll just ask you to sort of take a pause and just think about that, how beautiful the problem statement is, and how deceptively simple this whole thing is. Because come to think about it, that come to think about all of it, you're given an assembly of strangers or assembly of six people anywhere in the world, and what you're claiming is that you will be able to find out three people who all know each other, or yet three other people who do not know each other. So that's indeed a great revelation, and this is one of those tricks that you can always pull at a party, right? Indeed. So now I am going to headlong into the solution. So let me ask you this. Obviously, there is no way that you will be able to answer this question, but as soon as I put up this question to you, you should be able to answer this question in your head. So the question which I'm going to ask is that, how did we start the previous problem? Well, we said that, well, uh, say that human beings are dots, and those dots are called nodes, right? That's how we began, right? So I'm just going to do the same. So say that there are six people, and I'm going to call them as dots, represent them by dots. So A1, A2, A3, A4, A5, and A6. Right. Now, do you agree that either two people are going to know each other, in which case they are acquaintance, or they're not going to not know each other, in which this case they are strangers? So I'm going to draw a blue line. If there's a blue line between these two people, it means that these people in fact know each other. And if I join two people by a black line or black line segment, it means that these two people are strangers. So let this be our starting point. Right. So I'll ask you to examine this problem with respect to yourself. So which means that I'll ask you to examine this problem with respect to yourself. So suppose that you were the person A1. So how many people are you going to interact with? So well, you are going to interact with, in fact, six people, or rather five people. Uh, this guy, this guy, this guy, this guy, and this guy. Right? So you agree that from A1, we are going to draw five line segments. And all these five line segments will be either blue in color or they will be black in color. First of all, do we agree to this proposition that uh, all these five line segments that we are going to draw from A1, either they will be blue in color or they will be black in color? I'm hoping that the answer to that would be yes, because blue line segment denotes that A1 knows someone, or black means that A1 doesn't know someone. Right. And how many line segments are we going to draw from A1? So, well, there are five in total. Now, since there are five line segments to be drawn out of A1, and either they will be blue or they will be black, so do you agree that at least one of the colors must be at least three in number? So what I'm saying is that since there are five line segments to be drawn from A1, so at least one of these colors, blue or black, must be at least three. And the question to the at this point, you must be asking that why these colors, one of these colors, at least one of these colors must be at least three. So then I'll argue this way. Let's say that none of these colors are at least three. So if a quantity is not at least three, then it must be at most two, right? So this blue line segment must be at most two. Black line segment must be at most two. So then total number of line segments will be at most four, which is incorrect because the number of line segments emanating from A1 is five, right? Are we clear to this point? Yeah. So case which I'm making is that since you are going to draw 5 lines from A1 or 5 line segments from A1, so at least one of these colors must be 3 in number, because we have already proved that if at least one of these colors is not 3 in number, then both the colors must be at most 2 in number. And if they are at most 2 in number, then the total number of line segments will be at most 4, which is a contradiction because we are going to draw 5 line segments from A1, right? So now that we have made that clear, so what we're going to do is that, so pick your color. So because at least one of the colors is going to be 3, so I'll say that the number of blue line segments is 3. It doesn't really matter. Say that number of blue line segments is 3. So say that this is blue, which means that A1 and A3 know each other. And this is purely arbitrary. You can pick any two people and say that they know each other. Say that this is blue and say that this is blue, right? Since we have argued that at least one of these line segments must be 3 in number, so I have argued that let that be the color blue. So that's going to be 3 in number. Now I'll ask you to figure out, now I'll ask you to think of A4 and A6. Think about it. If you're going to join this by the color blue, if you're going to join A4 and A5 by the color A4 and A6 by the color blue, then do you agree that we are done? Why? Because we had to prove that there will be an assembly of 3 people who either know each other or either they do not know each other. So since this is a triangle of all blues, and by blue we mean that 2 people know each other, so we are done because all these 3 people know each other and we are done with the problem. So in that case, you might wish that, well, let this line segment in that case be not blue. Well, in that case, this line segment is going to be black. So A4 and A6 say that they do not know each other, right? Lovely. Then I'll ask you to consider A3 and A4. If you're going to join A3 and A4 by a blue line segment, or rather by a blue line segment, then I'm going to ask you to consider the triangle A1, A3, A4. Look at this triangle. Since this is a triangle of all blues, so it means that these 3 people, they all know each other. A1 knows A3, A3 knows A4, and A4 knows A1. So all these 3 people, they know each other. And well, we have proved the proposition as we set out to. Right, but so it's entirely possible for you to argue no. So which means that A4 and A3, they must not know each other. So they must not know each other means that they must be strangers. So you might add that A4 and A3 must be connected using a black line segment. And I am absolutely fine with it. Then I'm going to ask you to consider A3 and A6. What will you do regarding A3 and A6? If you're going to connect these 2 people by a blue line segment, if you're going to connect these people, these 2 nodes by a blue line segment, well, in that case, I'll ask you to consider the triangle A1, A3, and A6, right? Now, since this is a triangle which is all blue, it means that A1 knows A3, A3 knows A6, and A6 knows A1. And we are done with the problem because problem asked us to prove that there will be a group of 3 people who all know each other, or yet another 3 who don't know each other. In which case, you might argue that no, well, then do not color A3 and A6 using the blue color. In fact, color them using the black color. So you might be tempted into saying that what if A3 and A6 are joined using the color black? Well, in that case, I'm going to ask you to consider the triangle A3, A4, and A6. And you can see that this is all black. Since this triangle is all black, it means that A3, A4, they do not know each other. A4 and A6, they do not know each other. A3 and A6, they do not know each other. And which means that we have proved the proposition, right? So we're done. It doesn't matter how you are going to color A3 and A4. Doesn't really matter that how you're going to color A3 and A4. But you will always encounter a group of three people who either all know each other or yet group of another three people who do not know each other. And we are done with the proof. So in fact, I'll just add that these triangles of same color, they're called monochrome triangles or monochromatic triangles, if you like. And they form an important part of mathematics. And for those interested readers, uh, if you are really interested in what I have actually done, then you might go ahead and read more about Ramsey numbers. So that's that. So in fact, yeah, so we can take a few more cases, but that the proof will not be any different from what we have done in this one. So what I'm going to do is that I'm going to leave you with a couple of problems. In fact, uh, first of all, this, and uh, you might want to take a screenshot of this problem. And this seems to be a very interesting one that uh, if I were to give you a chocolate or a bar, which is of m by n size, um, and you want to break it into small pieces of 1 by 1, uh, how many steps would that require? What you can do also do is that, well, you can go tomorrow and buy some chocolates and experiment it yourself. Uh, you will have a great time. You will learn mathematics and will have a great time. And you will see that these are not two mutually exclusive things, right? So, and so this is, in fact, the problem. Uh, so that I wanted to take back home and try and come up with your own solution. Uh, come up with your own solution. So did you get the problem? So suppose that you have a chocolate and candy, or I don't know, like not a candy really, so something that can be further subdivided and something like that. And these all little squares are of the size 1 by 1. So how many steps does it require for you to be able to break it into chocolates of the size 1 by 1? And the question is that, does it depend upon how you break it? So for example, if and your sibling, or if you and your friend were to do it, uh, will they, so the number of steps that you will require to break this chocolate into the previous one, will this, the number of steps that you will take and the number of steps that your friend will take, are they going to be different or are they going to be the same? So that's the essential question which I'm leaving you with. And as I said, that you will realize that, well, mathematics can be interesting and you will have a lot of chocolates to eat. Right. So now what I'm going to do is that I'm going to take you to, in fact, uh, the course description, and I'm going to let you know that, in fact, how should you, in fact, uh, join these classes, how we're going to sort of begin these classes and how we're going to divide these classes into various bits. Right. So this is the Olympiad plan, and this is how we're going to do it. So, for example, this entire thing has been divided into about 70 lectures. So it's fundamentally divided into four sections: number theory, combinatorics, geometry, and algebra. Uh, so these are I have divided this entire program into two parts. So number theory one and number theory two. So number theory one means that the elementary part of number theory will be taken into the first course. The advanced part will be taken up in the second course, right? Uh, Same goes for algebra. You basically go with polynomials and such. And then there is algebra 2, in which we are going to take things further. So the course has been subdivided into two parts. In the first part, we are going to take up the very fundamental section. Uh, Obviously, we want to understand the fundamentals of any subject, but we also want to strengthen them to an extent that it will help us to prepare for what is about to come, that will be rigorous and uh, much at a much more higher level. So this is the plan for geometry, and this is the plan for combinatorics. So that's that's that. So that's the fundamental plan. So combinatorics means simply counting, and fancy word for it, counting. And geometry, here's geometry, and there is algebra, and then there was number theory. Now, the only thing which I'll state here before I leave is that should you commit yourself to this course, then you will have to devote enough time so that you can understand things your way, and you should be able to practice sufficiently large number of problems by yourself. As much as it's important to be attentive in the class and to solve the problems which I assign as homework, it should be incumbent upon you to solve problems on your own, because there should be an inherent love for you to be able to solve those difficult problems of mathematics and of Olympiads, right? Without that, you will be just attending these classes and maybe solving these problems, but you will be left behind all those serious candidates who are doing and solving problems on their own. So that's an essential requirement of this class. What are the prerequisites? So there are not many prerequisites, except that you should know basic addition, division, basic properties of divisibility and multiplication and such. So that's about that. So, okay, right. So that's all, folks, about today. And that was it. So, any update that happens to be from our side, you will receive it. Yeah. So, okay, that's all. And bye. Have a